Thank you all for being here. I'm Katie, I'm also from CCSE. And I'm also going to be talking about using low Mach number hydrodynamics, but on a slightly different scale. So this is work that we've started recently on ionic liquids within CCSE. So ionic liquids are solvent-free electrolytes, and the ones in particular we're interested in happen to be liquid at room temperatures. So not like molten salts like potassium chloride, where you would have to heat these materials up to large temperatures in order to get liquid-like properties, but ones that are have melting points below 373 Kelvin. So these are useful in a lot of technological applications. They're useful in organic synthesis and chromatography, extractions, but also in devices where one would want to have a high charge density. So examples would be solar cells, batteries, and supercapacitors. And they're composed of some example cations and anions on the left. And you see these are somewhat bulky electrolytes. And again, there's no solvent in these mixtures, so they can have maximal charge density. And in particular, for these types of devices, like batteries and solar cells, understanding the structures and properties of these materials at electrified interfaces is a challenging and important task that is useful for designing these types of applications. And so this is a snapshot of some of the work I'm going to show later. This picture on this slide is one of our simulations. And what you can see from the simulation is something that is known about these materials, namely that they are known to self-assemble into structures at the nanoscale. And the tuning of these structures, which you can do by changing the types of ions that go into making up these materials, will affect the mechanical charge transfer and transport properties of these materials. And understanding how we can tune that is important for applications. And in particular, a lot of the theory that has been developed to understand electrolyte solutions has been for dilute electrolytes and point ions. And these are not applicable for these very dense, bulky ions. So we need to proceed using a different route. And our starting point for this is going to be thermodynamic in nature. So this is a free energy functional meant to describe the interactions in these materials. So this is a function of concentration. We're assuming a two-component liquid, so C and 1 minus C fully describes which component is in the fluid. And it's a function of the electrostatic potential, which is going to be very important in determining the nature of these structures. So then the components that go into this free energy functional are listed here. So I'll take you through one by one. So first we have an ideal component of the fluid, which is just related to the entropy of mixing that you get when you put two components together. Then we have an excess free energy, which accounts for the interactions between these two different molecules in solution, ignoring the charges. So these are often polymeric-like materials. They have large hydrocarbon chains, and they'll want to phase separate. So putting in something that looks like a double well potential to mimic these particles' tendencies to separate into distinct components is what we put in with this excess free energy. We also have a gradient term that penalizes interfaces. So this is going to be related to the interfacial tension that you might get between having two different components making up this material. And then we have terms accounting for the electrostatic interactions in the system. So what's going to determine the patterns and from that the properties of these materials is this competition between the phase separating dynamics, which is encompassed in the excess Gibbs potential, and this interfacial term, and the electrostatic energy in the system. So that competition, this is going to want to smear out the charge. You don't want to have any concentrated charge too much in one region of the system. And this term wants to have these materials separate into distinct components. So that competition will determine the structure we get at the nanoscale. Then for the dynamics that we're actually evolving, we're using a fluctuating hydrodynamics model. So at the scales we're dealing at, which are nanoscale and micron scale, thermal fluctuations are important. So we put that into our hydrodynamics model. But again, it's a low Mach number, like Doreen just talked about. And we have to consider the species evolution, where again, C is the concentration of one of the components, rho is the density, F, I'll show you explicitly, is the species flux. And we get that's informed by our thermodynamic potential on the previous slide. We have to evolve the momentum of the fluid. So here U is the fluid velocity, P is the pressure, and then we have different components. Tau is our stress tensor, which I'll show you explicitly. Sigma is the Maxwell tensor, and R is an extra term that we again get out of our free energy functional that we introduced on the previous page. And we're assuming incompressibility for these systems. So what do these terms actually look like? To start with, the normal ones that you would expect just for a charged fluid without any of the thermodynamic information. We have a stress tensor that is composed of both a deterministic part, where eta is our viscosity, and a stochastic part, which comes because we're assuming that we're in a regime where fluctuations are important. Likewise, we have our Maxwell stress tensor, which you get from having a charged fluid. And in the absence of magnetic fields, this will just reduce to a Lorentz force on the fluid. Now the terms F and R are more special to this problem. We get them from considering what we put into our thermodynamic picture for this two-component ionic liquid. So the species flux comes from looking at derivatives of this free energy functional with respect to concentration, which we can use to define the chemical potential. And using formulations in irreversible thermodynamics, we can put in the transport coefficients, which are the Onsager coefficients, in front of the gradient of the chemical potential. And likewise, we have a stochastic term that balances this dissipative flux. This reversible term comes from having a two-component liquid, so we had this interfacial term in our free energy. And having this requires that we add this extra non-dissipative term to our momentum equation, which comes from a minimum action principle. So these are the terms that have been informed by our thermodynamic picture and that we can add into our hydrodynamic equations. Okay, so we also are trying to be true to reality. So we looked up what actual parameters are for these equations for a real ionic liquid, the one listed up there. And we can use that to inform our simulations and actually get an understanding of what real parameters are. And the parameters we do have control over are this excess free energy, which describes the tendency for molecules to phase separate, the two different molecules to phase separate, which I mentioned will be something like a double well potential, because we know that they want to be in separate phases, and also this kappa term, which controls the interfacial free energy in the system. So we can determine just by analysis of this equation, what do these things actually need to be, given the parameters from experiments that we are putting into this equation, in order to get the system to phase separate, meaning that if I set up a system that's homogeneous at C, so if I set up the concentration such that C is equal to 0.5 and I linearize that equation, that will be unstable, meaning it wants to separate into the two different types of species. And so we choose these parameters such that there is that phase separation tendency that will be competing with the electrostatic terms in the equation. Okay, so what does this actually look like? So first we can look at the model in the absence of charges. So I've mentioned we have this tendency for this model to want to phase separate into two separate components. So what you're looking at here is the density of one of those components. Red means very strongly enriched, blue means very strongly depleted. So this is a simulation that doesn't go to completion. If it did go to completion, you would see that it fully separates into red and blue, showing that the system in the absence of charges wants to form two distinct phases. So when we add the charges to this system, you see something quite different. These stripe-like patterns form that looks sort of like a microphase separation. It's not fully able to separate into two distinct components because that would be too strong of a charge penalty in this system. And we can actually look at what the approximate length of the average stripe width in this system is, and it's about 2 nanometers, which is consistent with scattering experiments for this particular ionic liquid. So that's promising. We get something that looks consistent with what people can actually measure experimentally for this ionic liquid. Okay, so one of the things that people are interested in particular for device design for these systems, and that has been discussed a lot in the literature recently, is how these materials actually behave at metal interfaces, so at an electrode. So there's good theory developed for dilute electrolytes, how they actually behave, how capacitance curves come out when you turn on an electrode next to an ionic solution. But people have shown experimentally that you get what they call anomalous capacitance curves when you do the same thing with ionic liquids. So to demonstrate, so In this drawing, I was told to say not everyone knows that plus is cations, minus are anions. So we have two types of molecules in this liquid. We've charged the electrode to be minus, so you get a pileup of positive cations at the electrode. And when we have a small surface charge, you can see that a dilute electrolyte and an ionic liquid actually behave quite similarly. So we're looking at the electric potential as we go away from the charged surface. And in the bulk, it eventually decays to zero to an electroneutral state. But right at the wall, you're going to have a pileup of the counterion to balance the charged electrode. When we turn up the surface charge on that system, the dilute electrolyte and it's reconnecting.
So, what's the size of the two zones, and how that compares to the number of elements in your mesh?
Oh yeah, that's an interesting question. Okay, so we have these stripes, right, and this is approximately 2 nanometers. So we have to use pretty small cell sizes. Ours are half a nanometer to actually capture this. And a good question is, we're using fluctuating hydrodynamics, and an assumption there is that we have a central limit theorem, that we have enough molecules in a cell to actually get Gaussian statistics. Doesn't actually, so we have like maybe 2 molecules per cell here. So that does seem to be an assumption that's maybe a little tentative, but we still, everything we expect, we use a structure factor to characterize are things working correctly, and they're working correctly as we can. So we can predict what the structure factor could look like, should look like, and it's consistent with that. So it's a good question. Okay, so back to this. Okay, so for a small surface charge on the electrode, the ionic liquid and a dilute electrolyte seem to behave very similarly, but when we increase that surface charge, you see that the dilute electrolyte decays much faster, and the ionic liquid is not, the electric potential from the ionic liquid is not decaying quite as much. And that's really because of how these molecules pile up at this electrode interface. And this is responsible for, you can use these plots that I showed on the previous page. If you take the derivative of the potential near the wall and scale that by the voltage you've applied across the electrode, you can use that to measure capacitance curves. And we know from theory and also from measurements that for dilute electrolytes, as you increase the surface potential on this metal electrode, the capacitance will increase linearly up to some point. And that's consistent with Gouy-Chapman theory, if you're familiar with that. For ionic liquids, because of how these molecules interact with the surface, they're just piling up more and more, and they form this extended double layer. Their capacitance measurements actually increase as we, or actually decrease as we increase the surface charge of the liquid. And this is something that people have referred to in the literature as anomalous differential capacitance. And our goal was to see if we could actually capture this with our model. So here we've added walls to the top and the bottom. And you can see that there's this buildup of the opposite charge, so this double layer development in our simulations. So this is consistent with what you would expect. And you can show that as you increase the surface charge, this double layer actually grows with surface potential. So this is also consistent with the theory that would predict this type of bell shape in the capacitance curves. And we can actually measure that. So if we look at, from our simulations, the potential as we put electrodes across the system and then vary the strength of the field, vary the surface charge in the system, we can look at a zoomed in section close to the wall and look at the scaled potential. And this gives us access to capacitance measurements, because if we look at the slope of this curve as a function of the field, that will recreate these capacitance curves that we were looking at on the previous slide by using this formula. And you can see that because the slope of the curves are decreasing as we increase the field strength, we are recovering this bell curve that we get for ionic liquids. So that, again, is another encouraging result. We are recovering this thing that's known experimentally for ionic liquids, and we get the correct size of the structures in these materials. So this is the summary and the future direction. So we think we have a model now that accurately reproduces some important experimental observations for these materials. And we really want to build on that to explore some of the phases potential in these materials. One thing that would be an obvious next step would be to use asymmetric ions. The phases actually get richer. We think they do if you have ions that are not the same mass or size, which is common in many of these materials that people are studying. 3D structures is something we're working on now because the phases can be more complex, the types of patterning that can develop. Additionally, we want to work on changing the boundary conditions because this behavior at the electrode wall is quite important, and depending on how these materials actually wet the electrode will influence these types of capacitance measurements as well, which will influence how mechanical properties and charge transfer properties and devices people want to develop. Additionally, we're interested in the dynamics of the charging processes, which are known to be interesting in these materials because they tend to be glassy. They're very viscous materials. So understanding how that affects the development of these patterns is something of experimental interest. And these are the people who have worked on this project. And with that, I'll take your questions. Thanks for dealing through the technological problems.
Say asymmetric, you mean the positives are different mass than the negatives? Or
Exactly.
You mean the molecules
Well, maybe both, but different masses to start, yeah. Any
I
other?
think this is going to be an obvious answer, but I'll ask it anyway. So 373 Kelvin was your magic number.
Room temperature?
Well, I said, okay, why 373 Kelvin?
That's room temperature? Or 273. Sorry, that's near room temperature.
Okay.
So we want them to be liquid at reasonable temperatures.
Is there a scientific basis, or is that sort of a technological target?
No, that they are actually usually room temperature, or sorry, they are usually liquids below that temperature.
I guess I'm trying to figure out which is causing. So these are things, like you said, it's not a solid. I would have to say that.
Yeah.
So you are looking at ones which have this behavior because you're interested in, because they're accessible experimentally, accessible technologically, or?
Well, because they're liquid, they're able to rearrange on timescales of interest. That would be if you're charging a device, like you want it to actually be able to rearrange. Am I answering your question?
Yeah. So when I was over visiting whatever the biological lab is downtown, right?
Okay.
They had a lot of bottles of this stuff around. I think they use them experimentally, so they need stuff that operates at room temperature, right?
Well, no, that's what I was asking. Is the motivation
Yeah.
for looking at this particular type sort of because it's accessible experimentally and potentially useful technologically, or is there some other fundamental thing that?
No. It's because it's probably technologically, yeah.
Okay, that's what makes it more
sorry.
interesting. Okay.
You wouldn't want to do something technologically with like potassium chloride, because
have to do high
it's like
temperatures.
over 1,000 degrees for it to be molten. So
Well, that's what I wasn't sure.
that
So
would be.
you've chosen this because they're accessible experimentally and,
Yeah.
and relevant technologically.
Yeah,
As
and
opposed to the fact that things over 1,000 just don't behave. I mean, like if you did, if they weren't room temperature, would it all be the same? Just
I don't
part of
think so,
development?
actually.
I might
Yeah.
add my 2 cents here. So these are typically used as solvents,
Yeah.
and you don't want too much energy going into melting them.
Yeah.
So they're alternate green solvents. And also another use for them is electric propellants. So you don't want chemicals to be heated to a high degree before they can be used as propellants. So
Yeah.
Right, which is saying yes to the previous
yes,
question.
they are
But I-
synthesized
And-
particularly to
But
remain.
suppose I looked at ones that were on average 100 degrees hotter.
That were, I think they would.
Would it behave kind of the same?
I
Sorry,
think
just a random
the
curiosity.
fact that they're bulky, right? Like they have like these hydrocarbon chains. I think that's important for this phenomena too. Like if you just had like more point-like ions, you can. I think
ahead.
John's like doing this right now. because we want to be able to measure the other types of curves. I think the fact that they're bulky imparts all this sort of structural charge correlation input to how they behave.
Okay.
We think, but film at the end of next week, that if I did the same thing, that capacitance thing, if I did that with molten potassium chloride, I would see the
Camel.
the camel, that extra hump, not the straight decay.
Okay.
Yeah. Any more questions? Thank-
Unfortunately, no.
Thank you.